Example 1 says, a snowball with radius 4 centimeters is melting at a rate of 3 centimeters cubed per minute. And it says, find the rate at which the radius of the sphere is changing. So this is a typical snowball problem. It's related to the balloon problem where as we change the size of the snowball or volume, the radius of that snowball or balloon changes. Now, some problems tell you the rate of change of the radius, and we have to figure out the volume. Other problems, like in this one here, we're given the rate of change of the volume, and we got to figure out the rate of change of the radius. Okay, so the first step is we want to connect the two variables in question. There is a radius and a volume that we need to connect. So we have a radius of 4 centimeters. We have the volume expression. We have volume here, so we need to connect that. And we're going to do that through the volume of a sphere formula. So the volume of a sphere formula looks like this. The volume as a function of radius is going to be 4 over 3 pi r cubed. Okay, so this is volume as a function of radius. So that's the very first thing we're going to do. Okay, so I want to then identify a few things here. I'm trying to find, well, I've been given 3 centimeters cubed per minute. That's a rate. That is dV by dt. 3 centimeters cubed per minute. You're being asked to find the rate of the radius. That is dr by dt. That's the unknown part. I need to differentiate this expression, this formula, with respect to time, okay? Because I need to introduce a dV by dt. So when I do that, I'm going to go dV by dt. Well, if I differentiate this expression with respect to r, I'm going to end up with, just color code this here, so this is dV by dt. I can differentiate the VR expression to get 4 pi r squared. Now this represents dV by dr. So I need to apply the chain rule here because r is a function of time. So I apply the chain rule. And applying the chain rule, I'm going to multiply by dr by dt. Now I don't know what that is, but I'm going to be able to solve for that now. So now I've differentiated with respect to time. I did apply the chain rule when I did that, and it generates all the parts I need. So at this point, I just need to figure out, plug in the parts that I know, and then solve for the unknown part. So I'm solving for the dr by dt. So I want to know dV by dt. That's been given to me, so I'm going to plug that in, 3 centimeters cubed per minute. And that's equal to 4 pi. Well, we've been given the r, the radius is 4 centimeters. So I'm going to plug that in. 4 centimeters for r, and I need to square that. Okay, 4 pi r squared. And then what's left then is my dr by dt. In fact, that's the only unknown quantity in this expression. So then I need to then solve for dr by dt by rearranging this expression. So I'm going to get dr by dt. Okay, so I'm going to do this is equal to, I'm going to take my 3 centimeters cubed per minute. I'm going to divide that by, it looks like 16 times 4 or 64 pi centimeters squared. Now you don't need to keep that track of the units, but I'm doing that anyway because I want to show that the units are consistent. So if you take a look at the units, I get centimeters in the numerator per minute in the denominator. That's the rate of change of my radius. Okay, I'm just gonna highlight that here. So that's all these units I just grouped together into here. And so what's left over then is I end up with 3 over 64 pi, and the units are going to be centimeters centimeters per minute. That's how fast the radius is changing. Okay, so that's my dr by dt, and it's approximately equal to, if I use my calculator here, it's going to be 3 divided by 64 pi, and that's going to be 0.0149. So I'm going to round that to 0.015. So 0.015 centimeters per minute.